In this video, we're gonna implement the double integration method to compute the deflection in a beam. So we're gonna look at an example. So the example we're going to look at is a propped cantilever. So it has a pin support on the left end. It has a roller along its length, and then it has a point load at the very right end. And we'll label the locations of the support as well as the location where the load is being applied. And we can also draw the deflected shape. So the goal in this example is to compute the vertical displacement at point C. Now let's put some dimensions on this beam. So the distance from the left end to the roller is 2A. And the distance between the roller and the point load is A. So the first step would be to come up with a free body diagram, which is relatively straightforward. We can just get the support reactions using statics, right? Sum of moments about point A, sum of forces in the Y. We can use that to compute the support reactions. And if we do that, we will get that the reaction at point B is 3/2P upwards, so it's positive, and then the reaction at A is going to be P/2 downwards, so negative, right? And then to complete the free body diagram, we'll also include the applied load. Right, so this is our free body diagram. So our next step would be to come up with our moment functions. And so because we have this support, this intermediate support along the length, we're actually going to have two moment functions for this beam. And so we'll define, so there'll be one moment function between points A and B and one moment function between points B and C. Right? So we'll first compute the moment function for AB. Right? And we can do that by just using equations of equilibrium. So we're gonna define the distance for the first moment function. We'll define the distance as x1. We're gonna say the moment at whatever cut section that we use is gonna be m1, and the shear is v1. And we know that on the left end, we know that the support reaction is P/2. And we can do the same for BC, right? So we can also, we also want to get a moment function for BC. So let's draw the associated free body diagram. So we have point A, we have point B. The distance we'll define as x2. We can add in our support reactions. And then the end moment and shear, which are unknown, we'll call M2 and B2 respectively. Let's also specify this dimension between A and B. Okay, so now we have the free body diagram. Actually, let's call this, because these are not the actual moment functions, these are just free body diagrams. So let's just call these, we'll call this the free body diagram for AB and the free body diagram for BC. So now let's start talking about let's now come up with the moment functions. So let's say moment function for AB, and so let's say we'll take sum of moments about the right end, right? So let's just call that sum of moments about the location x1. So we get m1 is equal to minus p over 2 x1. And this equation applies for x1 between 0 and 2a, right? Because again, this moment function only applies between a and b, and the distance between a and b is 2a. Then we can do the moment function for BC. All right, so we'll take sum of moments about x2, and we get the moment caused by the reaction at A plus the moment caused by the reaction at B. And if we rearrange that, we get M2 is equal to P x2 minus 3 P times A. And this moment function is applicable between for x2 between 2a and 3a. Okay, so now let's deal with the moment function for AB. So let's set up the equation for the moment function for AB. So what we're going to do let's rewrite expression for M1. And then we're going to replace M1. So let's go back a little bit. From this equation, we know that we can write M as EI times the curvature. So that's what we're going to do. Right, so we're going to place M1 with EI times the curvature, which is with respect to x1. and we'll call the associated displacement B1. So that's equal to minus P over 2 x1. And then if we integrate this equation once, we'll get EI times the first derivative. And so we just do the integral of this side, which we get minus P over 4 x1 squared plus C1, right? So we've introduced a constant because we integrated that right-hand side, and we'll call this equation 1. And then if we do a second integration, we get EI times B1 is equal to minus P over 12 x1 cubed plus C1 x1 plus C2. Okay, so now we're going to do the same thing for the expression. We're going to do the same thing for the moment function between B and C. So if you recall, the expression we got was M2 is equal to P times X2 minus 3 PA. And then what we're going to do is we're going to replace M2 with EI times the associated curvature. And we're going to call the associated transverse displacement B2. And we know that that moment function is also defined with respect to X2. So we'll call this equation 2. Okay, so if we take the first derivative, if we integrate once, we get this expression. And we'll call this constant C3, and we'll call this entire equation 3. And then if we integrate a second time, we get this expression. And we'll call this equation 4. Okay. So now we have 4 equations, and we also have 4 constants. So now we can implement, to solve for the constants, we can implement the boundary conditions as well as the continuity condition. So we're going to use 3 boundary conditions and 1 continuity equation and 1 continuity condition to solve for the constants. So the boundary conditions that we're going to use. So we know that at x1 equal to 0, we're at the left support. So that means the displacement has to be equal to 0. And then at x1 is equal to 2a, we're at the roller that's along the length of the, that's sort of intermediate between the two ends of the member. And so at that roller, the displacement also has to be 0. And then, so these two boundary conditions are related to the first moment function. We can also introduce another boundary condition associated with the second moment condition, which says that at the roller, the displacement B2 has to be equal to 0. And then, as I noted before, we're also going to use a continuity condition. And the one we're going to use says that the slope at the roller, based on the two moment functions, have to be equal to this, have to be the same. Right, so the slope for the first, based on the first moment function, has to be equal to the slope based on the second moment function at the roller support, where x1 and x2 is equal to 2a. One thing we can also keep in mind that is, by using these two boundary conditions, we're also utilizing the continuity condition that says the displacement based on the two moment functions has to be the same at the roller support, where x1 equal to x2, which is equal to 2a. Right, so these two conditions are the same, even though one is defined as a boundary condition and the other is defined as a continuity condition. Now, if we solve for, so now we've established 3 boundary conditions and 1 continuity condition. So that allows us to solve for the constants. When we do that, we get C1 is equal to PA squared over 3. We get C2 is equal to 0. C3 is equal to 10 over 3 PA squared. And C4 is equal to minus 2 PA. And then if we substitute, so if we go back, remember our goal is to compute the displacement at point C. So we can get the displacement at point C using equation 4, but we'll need to substitute the expressions for C3 and C4. So if we substitute C3 and C4 into equation 4, and we let x2 equal to 3a, right? Because we're trying to get the displacement at the very end of the member, we get BC is equal to minus PA cubed over EI. And this is what we were looking for, the displacement at point C. Keep in mind, we can also compute the displacement at any location, right, by just changing the value of x2 or x1 depending on which moment function we use or which displacement function we use. And we can also compute the rotation at any location, right? So for example, if we go back here, if we wanted to compute, say, the displacement between points A and B, we would use equation 1, where we'd have to substitute C1, and we would plug in x1 based on the location. If we wanted to compute if we wanted to compute the rotation between A and B, we would use equation 1. If we wanted to compute the displacement between A and B, we can use equation 2. In that case, we need to substitute the constant C1 and C2. And then if we want to compute the displacement or rotation between B and C, we would use equations 4 and 3 respectively while substituting the relevant constant.